This is my favorite steam vent tamer. Don't confuse it for a cool steam vent tamer. The steam that comes out of a steam vent is 500 degrees. As usual, I will first give you a quick tour so you can understand how it basically works, and then I'll get into some more details, and then I will build it using actual dupes so you can see how to accomplish that. I think the hardest thing about taming a steam vent is that they become overpressure really easily. You have to get the steam away from the steam vent in order to prevent them from becoming overpressure. I tried a bunch of strategies for making that happen, and this is the only one that I really like. I'm using 4 bypass pumps, one here, one here, one here, and one here. I have a video all about how these things work. The thumbnail says, I think, gas super pump. It's my most recent video. I'm sure you can go find it. What's happening is water comes out of this vent and it falls on top of this petroleum bead, that petroleum bead right there. When that happens, the water doesn't sit on top of the petroleum. The game moves it over here to this tile, and that displaces the steam that's in that tile. The steam does something strange. It moves diagonally up into this tile, up into here. Once it's up there, of course, it can go all up into this space and move on through the build to be turned into power at some point. So all 4 of these pumps are moving steam upward from that spot and that spot up into here, and from that spot up into there, and from that spot up into there. And once the steam is up there, it can't go back because the beads of petroleum are in the way. So what you end up with is a whole space up here above the bypass pumps that can be high pressure steam, and the space down below the bypass pumps is low pressure steam. That keeps the pressure around the steam vent quite low so it doesn't become overpressured. It turns out that bypass pumps are really good for this. They can move a lot of gas very quickly, and even the beefiest steam vent erupting the most possible amount of steam won't become overpressured. To keep the bypass pumps working, you need only very little water. These 4 pipes feed the bypass pumps, and there's 0.01 grams of water per second moving through those pipes. That means with all 4 of these bypass pumps running all of the time, it'll take something like 40 cycles to use just 1 full packet of water from a pipe. I should mention that I've seen this kind of a setup before using bypass pumps to keep a vent clear of pressure. The first place I saw it was by Math Mannequin on the Clay forums, and here's his version of the same thing using a cool steam vent. The bypass pumps do a great job of pressurizing all of the steam up into this area. There's a pressure limit of 1,000 kilograms in that area, because if you get above 1,000 kilograms, then these liquid vents can become overpressurized. And if that happens, then water won't be able to come out of the vent and the bypass pump will stop working. But that's something that shouldn't be a problem for this build. From there, the steam goes through this door compressor. The door compressor serves 2 purposes. The first one is that the steam that's up here is quite hot, and we don't want the steam to go through the door compressor faster than we can cool it down, because the steam down here is cooled down to our preferred operating temperature. If the steam down here gets above our preferred operating temperature, then the door compressor is disabled so that we don't keep adding hot steam. The other purpose of the door compressor is to keep the 2 chambers separate. The chamber up here has a maximum pressure of 1,000 kilograms per tile, and the chamber down here has no maximum pressure at all, none. That gives this build the capability of saving up as much steam as we want at whatever temperature we want for as long as we want in this lower chamber, and we can use it at our leisure instead of when we have to. After the steam goes through the door compressor, it goes into this area with the Aqua Tuner. The thermal sensor right here detects when the steam is hotter than we prefer it to be, and if it is, it enables this liquid shutoff to add water until the steam is the operating temperature that we prefer it to be. This is really good at making sure that the steam right here is exactly the right temperature that we want it to be for the steam that we're operating with our steam turbines. After the steam moves beyond that point, it doesn't undergo any more heating or cooling, so it stays just the right temperature that we want it to be for our steam turbines. The Aqua Tuner's job is to keep the steam turbines cool. It uses a basic cooling loop. The reason I put it at this location is so that it doesn't influence the temperature of the steam that's over here. I want a very exact working temperature for that steam. The liquid vent for the water that cools down the steam to the working temperature is right there. I've put it in a puddle of petroleum in order to avoid a bug that causes a lot of heat deletion in situations like this where you're adding water to high pressure steam. I currently think that using a puddle of petroleum like this is probably the best solution. It's about 95% efficient, meaning that it deletes about 5% of the heat. Notice that I've put some temp shift plates behind the Aqua Tuner in order to help keep the temperature nice and steady in this area. From there, the steam goes into this steam room underneath my steam turbines. I blocked some of the ports on the steam turbines because it turns out that managing water is really important when you're taming a steam vent. The more ports you block, then the higher temperature steam you can use to drive a steam turbine at its maximum power output. And the higher temperature steam you can use, then the less water that you need in order to cool down the hot steam coming from the steam vent. If you don't block any ports, then you have to cool the steam all the way down to 200 degrees, and you might not have enough water to do the job. When you do the math on that balance, the more ports you block, the better. For managing the water, it would be ideal to block 3 ports instead of just 2. But if you block 3 ports, then you need 358 degree steam in order to drive a steam turbine at its maximum capacity. And 358 degrees is too hot for a steel aqua tuner. So it seems like the sweet spot is to block just 2 ports. I blocked a third port on my second steam turbine for a completely different reason that I'll talk about later. The steam turbines process the steam and turn it into water. The water comes out of the steam turbines, and their first stop is to make sure the cooling loop is full. This only has to be done once, so it's not a big deal. The water's next stop is to go down this pipe and over this bridge to make sure the bypass pump stays supplied with water. The water's next stop is to go down from that bridge to the liquid shutoff. The liquid shutoff lets water through when the operating temperature of the steam gets too hot. And finally, if all of those pipes are full, then the water goes out this way to the rest of your base. Since this water comes from your steam turbines, it's 95 degrees. Sometimes I integrate cooling capabilities into a build like this, but I don't think it's a good idea for this one, and that's something I'll talk about later. There's a loop of water here that the Aqua Tuner uses to keep the steam turbines cool. This cooling loop is pretty simple. It has a bypass for the Aqua Tuner and 2 bridges that make a 1-packet buffer space to keep it all running smoothly. The wiring is straightforward. I have one wire that carries power out to my power grid and a wire that carries power in from my power grid. On average, this build will have a net power output of about 1100 watts, but it depends how powerful your steam vent happens to be. It can range anywhere from 768 to 1523. The automation seems a bit complicated at first, but it's really not too bad. This big complicated looking bit is just a controller for the door compressor. I'll show you how to make that and explain how it works. And this bit down here is just a controller for the aqua tuner that keeps the steam turbines cool. It uses a liquid pipe thermosensor to turn off the aqua tuner when the water in the pipe is sufficiently cold. This design is meant to run continuously, generating the same amount of power all of the time, even while the steam vent is dormant. I know this doesn't jive well with a lot of people's plans for their power grid. It is, in fact, preferential to be able to turn generators on and off depending on your power needs. But for a steam vent with steam turbines, I don't think that works very well. I think it's much better just to use your steam vent as a constant supply of power and use other generators in your base as a backup supply. The reason for that is that designing this so that you get a lot of power when you need it and none when you don't involves a lot more hardware and a lot more complication. First of all, you'll probably need about 2 more steam turbines. If you don't add more steam turbines, then saving up the power doesn't do you any good because you can't produce it faster than the steam vent makes it anyway. You also need some kind of backup supply of water at 95 degrees. If you don't use 95-degree water to cool down the steam, then some of this heat energy will go into warming up the water to 95 degrees. That energy can never be turned into power by the steam turbines because the steam turbines can't cool down steam to below 95 degrees. Also, this kind of power generation is difficult for dupes to access to make changes and repair things or for whatever reason. Other kinds of power generation, like petroleum generators or coal or even solar panels, they're much easier to get to and make modifications. For something like this, you will probably have to involve airlocks just to begin. Also, if you don't happen to run your steam turbines often enough, then your backup supply of 95-degree water will eventually run out. Your choices to fix that problem are to use cool water from your base, which wastes power because you have to warm the water up to 95 degrees, or use automation to turn the steam turbines on when you're out of water so that you can make sure that the incoming steam stays sufficiently cool. And that also wastes power in a setup like that. Ultimately, taming a steam vent so that you get a lot of power when you need it instead of a little power all of the time makes everything a lot bigger, a lot more complicated, and I just don't think it's worth it. Since I want to use this as a constant, reliable source of power, I consider making it so that it runs all the time, even when the steam vent is dormant, to be a really valuable feature. In order to accomplish that, we have to tune it so that it uses exactly the same amount of heat energy over the entire lifetime of the steam vent as the steam vent produces over its entire lifetime. In this case, with this particular steam vent, I have a total of 5 open ports on the steam turbines so that they consume about the same amount of heat that the steam vent creates over its lifetime. and slowly enough so that the energy that's stored in the heat and the steam down here will continue to last all the way through the steam vent's dormant period. In order to know how many ports to have open for your steam turbines, you have to start with how much steam your steam vent produces over its entire life cycle. This is a pretty useful thing to be able to work out for all of the different kinds of geysers and vents and volcanoes, and I'll show you how to do it, and it's not particularly hard. We're only going to use the numbers that are over here on the properties for the steam vent. Start with the amount of steam that it erupts while it's erupting. That's 2,456 grams per second. I like to work in kilograms, so I'm going to convert that into kilograms at 2.4563 kilograms per second. Then multiply by how long it erupts for. That's this number right here, 366 seconds. So times 366 seconds. And then divide by the total amount of time between those eruptions, 717 seconds, divided by 717. That gives you the amount of steam that it produces during the steam vent's active period. It doesn't count the dormant period. Multiply by the length of its active period, 97.2, 97.2, and then divide by the total length of its entire cycle, divided by 155.7. And that'll give you the average amount of steam that it produces over its entire lifetime. And in this case, with this particular steam vent, it's 0.7827 kilograms per second. Just to recap, start with that first number, and then multiply, divide, multiply, divide. And that'll give you the answers that you're looking for. Now that we have the average amount of steam that the steam vent produces, we can work out the average amount of heat energy that the steam vent produces, and we can figure out how much heat energy the steam turbines have to delete, and that lets us work out how much heat the steam turbines themselves produce, and that lets us work out how much heat the Aqua Tuner produces, and ultimately the total amount of heat produced in the system, and therefore how many ports to have open on the steam turbines in order to delete that heat at the correct rate. And all of that math is a giant pain, but don't worry because I've made a chart for you. Here it is. This particular steam vent produces 783 grams per second of steam. That range is right here, so we need a total of 2 steam turbines and a total of 5 ports open. As you can see in this particular build, that's what I've done. There's a total of 5 ports open. That's why I blocked the 3rd port on this steam turbine. Unfortunately, even after all of that, it's still not quite right. We've had to round up to the nearest number of ports. So ultimately, these steam turbines would be consuming too much heat energy, and we're going to run out of steam before the dormant period is over. Luckily, there's an easy way to dial back the amount of heat energy being consumed by the steam turbine so that you can get it exactly right, and that is just decrease the temperature of the steam. We can figure out exactly what that temperature should be by using a whole bunch more complicated math, but don't worry, I made a chart for this as well. So here's that chart. This particular steam vent produces 783 grams per second. So if we just find 783 in these numbers, here's 783, and then go to the top of the chart, it'll have a number there for the temperature. In this case, it's 264. So if we set the thermosensor down here to 264, which it is, then these steam turbines will consume exactly the amount of heat they need to in order to run all of the time, even through the steam vent's dormant period, and produce that nice constant power. I will put links to my charts in the description in case you would like to do it that way as well. Over a very long time, hundreds of cycles, I think that you can expect the pressure of steam in this room to stabilize at somewhere between 2 and 3,000 kilograms per tile. The reason that happens is because as the steam pressure increases, your heat efficiency decreases very slightly. This has to do with the way the water is added to the steam in order to cool it down. I think the difference is only about 1/4%, so it's not very significant, but it's enough to get the steam pressure to stabilize. Unfortunately, all of that is very hard to test because it would require letting steam vents run through multiple life cycles, and I don't have the patience for it. So if you have feedback, give me feedback, and we'll see if the veracity is good. Alright, up next, let me show you how to do the automation for the door compressors. Let's suppose we have a room, something like this, and we want to compress all the gases from the top of the room into the bottom of the room. So similar to what we're doing in the steam vent build. I'm using 3 doors for the compressor, so I'm going to go with that. And I'll hook up some power to it. The first thing to do is to decide what you want the door compressor to look like when it's idle. So which doors are open and which doors are closed. And in the case of what we're doing here, I keep the top two doors open when it's idle and the bottom door closed. That way the two steam areas stay separate, but the top doors can fill up with steam while it's not doing anything, so it's ready to go. So once you've decided that, put a NOT gate next to the doors that you want to stay open when the door compressor is idle. And I'll hook that up with an automation wire. Like that. So now this is the idle state of our door compressor. Each time the door compressor cycles, each of these doors will be able to open once and close once. Or I guess in the case for the ones that are already open, they'll have a chance to close once and then open once. You need each of them to wait a certain amount of time before they make their first move. And in order to decide how much time that is, you can put a filter gate on each one of them. There, and there. And I'll hook those up with the automation wire. Each door also needs to wait a certain amount of time before it makes its second move. For example, for this door, the filter gate decides how long it waits until it opens, and I can use a buffer gate to decide how long it waits until it closes. So I'll stick a buffer gate on each door. And I'll connect those with automation wires. Now we need something to decide when a cycle starts, and for that you can just use a timer. Like if you want the door compressor to cycle every 5 seconds, you need a timer that goes off every 5 seconds. You can make an easy timer with a buffer gate and a NOT gate. Just face them opposite directions like this, and connect their inputs and outputs together. What that does is every 5 seconds, because the buffer gate is set to 5 seconds, this red wire will flash green for just a moment, and also every 5 seconds, this green wire will flash red for just a moment. We can connect the red wire to the buffer gates, and every 5 seconds it will start the cycle. Every 5 seconds, these buffer gates turn on and they last until they expire. Those are all of the gates that we need for the door compressor to work. The only thing left is to set the times on the filter gates and buffer gates so that the doors open and close in a reasonable sequence that makes sense. I'm going to disconnect the timer for now so it's not distracting while we think through those times. All you have to do to set up the times is think through what you want to happen in the door compressor at each second of the cycle. The first thing I want to happen is for the top door to close, and that can happen immediately when the cycle starts. So I want this filter gate set to 0. So I'm just going to take the filter gate out completely and connect it with a wire. That's the same thing as a filter gate that waits 0 amount of time. So the top door closes immediately. After that happens, I want the bottom door to open. So after 1 second, I want the bottom door to open. I'll set this filter gate to 1 second. On the second, I want the middle door to close. So I'll set its filter gate to 2 seconds. On the third second, I can open the top door and I can close the bottom door. So I'll set the buffer gate on the top door to 3 seconds, and I'll set the buffer gate on the bottom door to 3 seconds. And on the fourth second, I can open the middle door. So I'll set the buffer gate for the middle door to 4 seconds. Since it takes a total of 4 seconds to cycle all of the doors, it makes sense to leave the timer at its default of 5 seconds so that a new cycle starts after 5 seconds. Now I'll just connect the automation wire and that should do the job. When the timer starts the cycle, the first thing that happens is the top door closes. The next thing that happens is the bottom door opens. The next thing that happens is that the middle door closes. And the next thing that happens is the top door opens, because why not? We might as well let gases start going in there. And also the bottom door closes. That pushes the gases the rest of the way out the bottom of the door compressor. The next thing that happens is the middle door opens, and we've returned to the idle state of the door compressor, which means as soon as the timer goes off again, it will start the same process over. And there it is. If you want to disable the door compressor so it stays in its idle state, you can just make sure that this wire on the timer stays green. That will prevent the timer from making the green flash that starts a cycle of the door compressor. I can demonstrate that by putting a signal switch right here and connecting it with an automation wire. The signal switch is set to green, so the timer doesn't work anymore and the door compressor stops in its idle position. If I turn off the signal switch, then the timer continues and the door compressor keeps working. And if I turn it on again, then the door compressor finishes its current cycle and doesn't start a new one. If you prefer to memorize the numbers for all of the gates, then you can remember that this one is 1 second, this one is 2 seconds, this one is 3, 4, and 3, and the timer goes off every 5 seconds. This is all exactly the same as the setup that I use in the steam vent build. These are my gates for controlling the doors. I have a timer right up here, and I disable the door compressor using this Atmos sensor, which detects when there isn't enough steam up here in the room to bother running the door compressor. I also disable the door compressor when the thermosensor in here indicates that the steam in this room is too hot. That's because I don't want to be adding new 500-degree steam down here until the temperature is where I want it to be. You'll notice that I put a buffer gate on that wire. That serves two purposes. The main one is that the Atmos sensor and the timer over here would use that wire to control the liquid shutoff that cools down the steam if there weren't a gate between them. I decided to use a buffer gate because I like the idea of making sure that the temperature of the steam down here is good and stable before the door compressor starts running again. Using the buffer gate means that the temperature has to be stable for at least 5 seconds before the door compressor will be activated. I think that's all the explanation I need to demonstrate how everything works. Now I'm going to demonstrate how to build it with duplicates so you can see a process that works in order to complete this successfully. In the build I do with duplicates, I'm going to make this room one tile higher, and that's so that there's enough space in here for duplicates to get in and out without having to make special airlocks and stuff. I've already set up an airlock over here and an airlock over here, and the idea is once this area becomes a vacuum, my duplicates will still be able to get in and out, and also over here, this area will eventually be a vacuum and my duplicates will be able to get in and out of there. The plan is to start building tiles first along the bottom and then a layer at a time, working my way up through the build. The places that I want to be a vacuum, I will fill in with regular tiles, and then later I can deconstruct those tiles in order to leave a vacuum in its place. I made the steam vent so that it looks typical for what they look like after I've discovered them on my map and dug them out a little bit so that I can see a bit of the steam vent and identify it. So let's let my dupes get started on the floor. I'm making the insulated tiles out of ceramic. I think you can probably get by with mafic rock just fine. It's a pretty good insulator. Now I have a problem where the steam vent is. I can't build a tile in this spot because the steam vent blocks me from doing it. So I'm going to fill in that tile with water instead. The water will displace the oxygen and make it possible for me to make a vacuum in this area. My bottle emptier over here is done, so I'm going to have my dupes deliver some water to it. This area up here will be my steam room, and I don't have to make it a vacuum, so I'm just going to build it right in. Water has been delivered to this bottle emptier, so I don't need it anymore. I know I need some wires in these mechanized airlocks, and I also know that my dupes will have a hard time reaching them once I've built these tiles. So I'm going to put those in right now. Power wires, and also the automation wires for the gates that I'm going to put there. Now that all of the tiles are in, I can hollow out these areas and they will be a vacuum. Be careful not to deconstruct any of the tiles that make up your airlock. Also, you can dig out the steam vent now, but you want to leave the tile right in this spot. That's the one that prevents the steam vent from erupting. So notice that since all of these tiles are behind the airlock, gases can't get in, and as I remove the tiles in here, it's a vacuum. I need to get some petroleum down in this little well, so I'm going to put in a bottle emptier to deliver that. The liquid valves up above this that provide water to the bypass pumps. I'm going to make those out of gold amalgam. That's because liquid valves can overheat, and these will eventually be carrying water that is 95 degrees. So the room that they're in will eventually be 95 degrees, and I don't want them to overheat. There's petroleum in this well, so I don't need the bottle emptier anymore. We need an aqua tuner made of steel. I really like aluminum for this, but I think any temp shift plate will do the job just fine. I'm going to position the temp shift plates where they don't interact with the insulation too much. I'll put 3 of them right there, and I think that'll do the job nicely. I have a couple of tiles up here that my dupes can't deconstruct because they can't reach them. I think I can probably solve that just by putting in a couple of ladders like this. I think it's simplest if you hook up the generators so that they send power out to your power grid, and you hook up everything else so that it brings power in from the power grid, instead of trying to integrate these together. But for this demo, I don't have a power grid to connect to, and I need some amount of power in order to get the build started. So I'm just going to connect all of these together and use a mod to provide power to it. Let's blueprint in all of the plumbing now. This build needs a double bridge as a buffer for this particular loop. The idea is when you put 2 bridges over each other like this, and you connect their inputs together and you connect their outputs together, but not between them, then that creates one space in a pipe right here underneath this liquid input that acts as a buffer. When there isn't enough water, then it skips over that pipe, and when there's one packet too much, then that packet will go into that pipe. I see there's still a tile here that I want to deconstruct, but my dupes can't reach it. I can reach that tile by deconstructing this insulated tile, and that won't break anything, and my dupes will be able to reach through the hole and deconstruct the tile. Let's put in the automation. In case you think this is going way too fast, I explained how to make this earlier in the video. I'm just going to connect the liquid pipe thermosensor to the Aqua Tuner, and I like to put a filter gate in there so the Aqua Tuner, once it's off, stays off for at least 5 seconds. That way it doesn't turn on and off a lot. We need to get some petroleum beads on these tiles here, 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 and here in order for the bypass pumps to work. I didn't plan for that very well. I think I'm going to have to take out a couple of these liquid vents in order to make a place for a bottle emptier to sit on each side. And now I'm going to use some mesh tiles to make a place for a bottle emptiers to sit over here so that I can get the petroleum that I need in this room. Everything that we need in this steam room is complete, except that I need to know how many ports on the steam turbines that I need to block in order to be tuned properly for this steam vent. On this map, I've cheated. This steam vent is already analyzed, but normally you can't analyze it until the steam vent is unblocked. There shouldn't be any harm in letting the steam erupt at this point, so I'm going to dig out this last tile. I'm ready to start delivering petroleum to these tiles so that I can get my bypass pumps to work. I'm going to put a bottle emptier right there and a bottle emptier right there. The bottle emptier can put petroleum on this tile, and some of it will run off onto that tile, and then I can mop up the extra off the bottom. The same thing will happen on the other side. Also, I think Joshua is stuck. So the steam vent is unblocked now, so the dupes can start analyzing it and find out how much steam it produces on average. We've delivered some petroleum to this, so we don't need it anymore. I will deconstruct it and the mesh tile below it. I see my dupes can't really reach this other bottle emptier. I'm going to give them access by deconstructing. I'll deconstruct this tile and that tile, and that should work. I have a problem. I deconstructed the tile that the petroleum is supposed to land on for the bypass pump. Clearly they can't reach that bottle emptier. Clearly it's kind of a pain to get the petroleum in the right place over here. I'm going to deconstruct these two tiles and put ladders in their place so my dupes can reach that. Alright, we finally have petroleum where we want it to go. I don't need this bottle emptier anymore or the mesh tile underneath it, and I can make these two ladders back into insulated tiles. Let's set up the liquid valves. They need to be 0.1 grams of water each. I want to wrap the valves in insulation. They'll be carrying water that's 95 degrees eventually, and I'd rather not have that heat escape into my base. Now let's tune the build to match the steam vent. What we need to know is what the average output of steam is for this steam vent over its entire life cycle. So I'll get my calculator out. It produces 2.3801 kilograms per second. times 392 seconds every 779 seconds. So times 392 divided by 779. And its active period 84.4 cycles every 125.9 cycles. So times 84.4 divided by 125.9. This steam vent produces 0.803 kilograms per second of steam over its entire life cycle. That's the number that we needed to know. With that number, we can use those charts that I made in order to figure out how many ports we need open on the steam turbines and what temperature steam we want them to operate with. So 803 grams per second. If you look on this chart, 803 means we need 2 steam turbines with a total of 5 ports open. Right now we have a total of 6 ports open, 3 for each steam turbine, so let's block one of those so that we only have 5. We can use the other chart to determine what temperature steam we should be working with. That's this chart. Let's find 803 grams per second. The numbers are kind of in order and kind of not in order. Here's 803, so we want steam that is 268 degrees. So I'll set the thermosensor here to 268 degrees. And we're ready to start up the build. The way to start the build is to add water to it. You can add water to it right here. I don't have a source of water for pipes in this sandbox space, so I'm just going to use a mod that produces it for me. Now water is going into the build. The first thing it will do is fill up the cooling loop. We need to finish setting all of the settings for the stuff in here. Let's set the thermosensor to above 14 degrees. That will prevent the thermo aqua tuner from cooling the water and freezing it and breaking the pipes. And we can set this atmo sensor to disable the door compressor if the pressure in this room is below, let's say, 3 kilograms. We also need to set up the times on all of the gates that control the door compressor. I've memorized these, so this is a 1, this one's a 2, this one is 3, this one's 4, and this one's 3. And for the timer on the door compressor, I can leave it at its default of 5 seconds. Now the water is following this pipe and it will get the bypass pump started. I see I didn't set up this thermosensor quite right. It should let water in if the temperature is above 268 degrees. So we don't need to keep adding this water anymore. We have enough. I'm going to let my dupes in to clean that up. I see I made a mistake with the bypass pump over here. Bypass pumps prefer to move gases from the right up above them, so I need to build another tile right here in order to force the bypass pump to go to the left to move gases, and I will deconstruct the tiles in this wall so that my dupes can get in there and get the job done. Everything has warmed up enough at this point that we're starting to get some proper steam down here in the steam room. The other steam turbine came on, so that's a good sign. Got hot enough down here in the steam room that the water that was in there evaporated away, and it's the temperature is still increasing. So something interesting happened. Our steam turbines got caught up and cleared all of the steam out of the steam room down here. That's kind of something I would expect while it's warming up because we're not adding water to the 500-degree steam to keep it cool. So we end up with less steam than normal. I'll tell you what I don't understand is where did this water come from? Seems like the only possibility is that something cooled the steam down, but there's nothing in here. I mean, stuff over here is 200 and something degrees. So are the temp shift plates, so is the petroleum. It couldn't have possibly been that, and there's nothing else in this room. Maybe it's this rock. Oh, it is the rock. That's bad because they will continue to cool things down around them a little bit until they warm up to the temperature of the steam, and it takes them a long time to warm up to that temperature. So that's an interesting problem. In the long run, it makes absolutely no difference, but you might want to take extra steps to remove debris from these rooms when you build this thing. For the sake of the demo, I'm going to cheat and just remove it. Then we can see how this ought to work if you did a better job of setting it up than I did. I think the build is mostly warmed up now. It looks like it's going to clear out the steam again. But now that everything is essentially up to the temperature that we want it, it's going to have to start adding water in order to keep the temperature low. And I think that'll be the last time that we get very low steam pressure in this room. Okay, this all looks pretty good to me. The steam pressure is on the rise. After every eruption, it's increased more and more. The steam temperature is, well, it's not entirely stable yet, but the steam pressure is still pretty low. The steam turbines are producing about the right amount of power that they should be. This one is near its maximum, and this is a third less than that because it has one of its ports blocked. The build is tuned so that it can last all the way through the dormant period without running out of power. But remember, when you first turn it on, if you don't do it before the beginning of the steam vent's active period, then you don't have enough time to build up that extra heat energy. So the first time, you probably will run out of steam sometime during the dormant period. But once the steam vent becomes active again, you should never have to worry about it again. I wonder if the debris over here is still stealing my heat. Ooh, 337? Well, I guess it is because the stuff in here is supposed to be 500 degrees, so I'm actually still wasting some heat energy on warming up the debris in this room. I suppose you should do a better job than me when you set this up and sweep out the debris before you get it started. I think I'm going to start making blueprints and save game files, so I'll put links to those in the description, plus links to my charts, and anything else that I can think of. Thank you for watching, and I will see you for the next one.